Okay, so the next element that I want to talk about in electrical circuits are resistors. And as I talked about in batteries, as that potential energy of a battery is used up, it dies. That was the end of the last episode. So if I had a circuit where the current is really, really high, all those charges are going to flow immediately to the other side and your battery is going to die. And a lot of energy would be released very quickly. And I talked about how when energy is released very quickly, wires get hot, batteries get hot, and we can cause a fire. In fact, certain elements such as a light bulb, if it heats up too fast, it's going to break, and I'm sure you've seen that before. So we use resistors, which is a component that would slow down the current flowing through a circuit and prolong the life of a battery. If we don't have resistors in a circuit, the battery would die really, really quickly. And we can see that using Ohm's law. So if I had a battery that is 9 volts and a resistor that is 10 ohms, okay, according to Ohm's law, the current in the circuit is going to be 9 volts divided by 10 ohms is going to be the current. Okay, and all I did was I rearranged that equation. V divided by R is equal to I. Okay, so what we can see here is the greater the resistance, the smaller the current is going to be. And in this case, in that circuit, the current would be 0.9 amperes. Okay, so if I really want to slow down the flow of charge in a circuit and prolong the life of a battery, I would increase the resistor. Problem is, if my resistance is too high, that flow of charge is so slow that very low amount of energy is going through that circuit. So we have to play with a balance of current, okay, and a balance of storage of charge in a battery and a balance of resistance. Okay, so what's inside of a resistor that allows it to impede the flow of charge in a circuit? And inside of a resistor, if you ever opened up an electronic device, you would find these little components in there. Those are resistors, and these little colored lines represent the amount of ohms that each resistor has. We'll learn more about that next year in grade 11. And if I crack that casing open, I would see that some of these resistors have different materials inside. Okay, some have carbon, some have carbon mixed with some other types of ceramic materials, and some are just wrapped around with wire. This particular one would be used for heating. That's nichrome wire. Okay, so as electricity goes through, heat would be generated, and these other ones might have a lot higher resistance and really slow down the current. Okay, and as we talked about before in a previous video, the relationship between resistance in any material depends on the nature of the material. That's resistivity, and resistivity depends on the nature of the material. Okay, it's like specific heat capacity. The length, the longer that material, the more resistance it's going to have. And the greater the cross-sectional area, the less resistance it's going to have. So a thin wire has a lot of resistance. Okay, a long wire has a lot of resistance. So the way we make resistors is we wind, for example, this case, I'd wind a longer length of wire inside to increase the resistance until I get what I want. Okay, if I want to lower it, I use a thicker wire that would make a larger area that would decrease the resistance. Okay, so people who manufacture these components would play around with that equation to calculate the resistance that they need for that component. Okay, and remember, you plug that back into Ohm's law. Depending on how much current I want in my circuit for that voltage, I can then make a resistor with the appropriate amount of resistance using this formula. And you guys are doing a lab on this formula where we're going to be measuring the resistivity, that variable of carbon. Okay, so you're going to have a length of carbon and you're going to be measuring the resistivity from a graph. All right, and we'll talk about that in class. All right, so if I take different materials, how does their resistivity, how does that value right over here differ when I have carbon, ceramic, or nichrome? So here you can see a bunch of different metals. You got nichrome in there and you got carbon. And if I take a look at their resistivity, that rho value, you can see that it goes from small to high. Okay? The smaller the resistivity, the more conductive that material actually is. Okay, so copper is more conductive than aluminum. Okay? All right, so we have different materials in here with the different resistivities. And carbon, that's quite resistive. Okay, that's why we don't really conduct electricity that well. Okay, and nichrome is a very resistant metal. Okay, we'll use that for heating, which I'll talk about in a second. All right, so somebody who's designing a resistor is going to choose which material they want to use and the properties of those materials based on the resistivity, and then build a component using this equation to create the appropriate resistance for the Ohm's law formula. Okay, so how are resistors used in heating circuits? Well, like I said, okay, the resistor slows down the current in a circuit. All right, and then what I said in a previous video when we talked about batteries is that when charge flows through a circuit, so if I have a positive charge that's flowing through the circuit, in order for that, when that charge comes back to the other side of the terminal, it has to spend 110 joules of energy per coulomb of charge. So for every coulomb of charge that flows through that circuit, 110 joules of energy has to be spent. And if I use an appropriate amount of resistance, a lot more resistance here, all energy is spent here. Oh, I can never spell across. Okay, so all the energy used, okay, from that 110 joules per coulomb, if this is the only component I have in my circuit, all 110 joules are going to be used to push that charge across the resistor. It's going to bounce around. It's going to bump into all the atoms in there. And then all that 110 joules is used as work, and that work is used to raise the kinetic energy of the atoms inside and is released as heat. Okay? So I need to know how many coulombs of charge flows through that resistor in a second to find out the total amount of energy that's produced by a resistor. So if I had my fingers on a resistor as I've plugged it in, what you'll notice is it's going to get hot. And if there's a lot of current, it's going to get hotter faster. Okay, so we describe the power, the amount of energy produced by a resistor per second is the formula I presented before. Power is equal to joules per second, which is equal to my volts in a circuit multiplied by my current. All right, and if I take a look at this little video here, you'll see two different circuits. Okay, one that's doing work very slowly and one that's doing work a lot faster. Okay, so this cell phone on the left is doing a lot of work faster. That cell phone would have a circuit that would have a very high current. They both have the same battery, but the current in that circuit would be a lot faster. So higher current, same volts, and it has more power. But the byproduct of that power is that it's using its energy a lot faster than the other battery, and so it dies quicker. Okay, so power would be the voltage of the battery inside the circuit times the current. All right, and if I go back to this electrical heater, how would I be able to calculate the current? I have the voltage, so V equals IR. So I have 110 volts divided by 10 ohms is going to give me 11 amperes. Okay, so my current in that circuit there is 11 amperes. So if I want to calculate how much heat is produced in that resistor per second, I can then plug that into this formula. So 110 volts times 11 amperes, okay, is going to give me a lot. Okay, it's going to give me 1,100 joules per second plus 110 joules per second. See how I did that mental math? 11 times 110. And that gives me 1,210 joules per second, or 1,210 watts, if you remember from when we talked about power in the mechanics unit. So what that means is that circuit is going to produce 1,210 joules of heat per second. So if I have that circuit inside of a cup of water, now you'd never do that because you can get electrocuted, but if that's water, okay? And I'm heating up that water. Okay, that water is going to receive 1,210 joules of heat, I'm saying Q, per second. And then I'd be able to use MC delta T to calculate the change in temperature of water. And that's how we would use a resistor in a heating circuit, okay? So just to go over that again, okay, the resistor slows the flow of current through a circuit. And all that energy, if this is the only component, all the energy, 110 joules per coulomb, is going to be released as heat energy in the circuit. Okay, and to calculate the power of that heat energy, I need to take the volts applied times the current. So in order to calculate the current, my voltage divided by my resistance is going to give me my current. And then 110 volts times 11 amperes gives me 1,210 joules per second, or 1,210 watts. And all of that heat energy is going to go into heating water.